Hello, and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be estimating the value of irrational square roots and then plotting those square roots on a number line. Before we do, let's look at a few definitions. Now, in previous courses, you learned about squares, square roots, and perfect squares. But let's just do a brief overview on these terms. When we square a number, we are raising it to the power of 2 and multiplying it by itself. When we take the square root of a number, we are doing the opposite or inverse operation. When we square a whole number, we will get a perfect square. For example, if I square the whole number 5, 5 squared is 25. So 25 is called a perfect square. The square root of a perfect square will always be a rational number because it can be rewritten as the ratio of two integers. For example, the square root of 64 is equal to 8. And 8 is a rational number because it can be rewritten as 8 over 1. Now, irrational numbers are numbers whose square roots do not result in whole numbers and therefore cannot be written as the ratio of two integers. Irrational numbers have decimal equivalents that do not repeat or terminate. Square roots of non-perfect squares are examples of irrational numbers. So, square roots such as square root 2, square root 10, and square root 15, those are not square roots of perfect squares and therefore are irrational. So in example 1, it says determine whether each square root is rational, R, or irrational, I. So to do this, we're going to use our calculator. So if I type in square root 7, I get a decimal, that does not repeat or terminate. So this would be an irrational square root. However, if I take the square root of 49, I get a whole number, 7. So that is a rational number because 7 can be rewritten as the ratio of two integers. And anything that can be rewritten as the ratio of two integers is a rational number. All right, square root 101 gives us a decimal that does not repeat or terminate. So it is an irrational number. Now, square root of 169 is a whole number. So it is a rational number. So we have rational square roots, like square root 169, and we have irrational square roots, such as square root of 101. Example 2. A student solved the equation x squared is equal to 120 to find the length of the diagonal of a square in centimeters. Find the length rounded to the nearest tenth. So if the student was solving this equation, let's rewrite it. They would need to do the opposite or inverse operation in order to solve it. Well, in our box above, we learned that the inverse or opposite of squaring a number is to square root the number. So the inverse of x squared is square root of x squared. And if we take the square root of one side, we must take the square root of the other side. So the square root of x squared is x. And then the square root of 120, we'll put that in our calculator. And they want us to round this to the nearest tenth. So this would be 10.95 would round to approximately 11 centimeters. Example 3. The area of a square wall is 180 square feet. What is the side length in feet of this wall? round your answer to the nearest tenth. So here we have a square where all the sides are the same. We know that the area is 180 square feet. What they're asking us to find is this side length. So the formula for the area of a square is area equals side squared. Now in this problem, we don't know the length of the side, but we do know the area. So I can plug in that number for A, and I get this formula, 180 equals s squared. Now when I'm solving an equation, I like the variable to be on the left. So I'm going to rewrite this. And I'm not going to change anything except the order. I'm going to put the variable s squared on the left and the number 180 on the right. Now we're going to solve this problem just like we did in example 2. The inverse operation for squaring is square root. So I'm going to take the square root of s squared, and if I take the square root of one side, I have to take the square root of the other side. So the square root of s squared is s, and then the square root of 180 is approximately 13.4 feet. So I know that each side is approximately 13.4. So if I were to do 13.4 squared, I should get something close to 180. 179.56, which would round to 180. So we know our answer is correct. Now, one important skill to have is to be able to estimate irrational square roots so that you can approximate its value. So for irrational square roots, we can estimate their value by using two consecutive perfect squares and their related square roots. List the first 15 perfect squares below. So we know that 1 squared, or 1 times 1 is 1, 2 squared is 4, 3 squared is 9, 4 squared, 16, 5 squared, 25, 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared is 100, 11 squared, 121, 12 squared is 144, 13 squared, 169, 14 squared, 196, and 15 squared, 225. Now, we're going to use these perfect squares to help us find the value of square roots that are not perfect squares. So look at example 4. Use a number line and your knowledge of rational square roots to estimate each square root. So in problem A, they want us to estimate the value of square root 29. So what you're going to do is you're going to look in the list we just made, and I want you to find a perfect square that's just a little bit smaller than square root 29. I want a perfect square that's a little bit smaller than square root 29. So hopefully you said square root 25 is a little bit smaller than square root 29. Then the next perfect square after 25 is square root 36. So we know the square root of 25 is 5, and the square root of 36 is 6. So I know the square root of 29 is going to be a number that's between 5 and 6. So let's plot it on the number line. So where should I plot the square root of 29? Should I plot it closer to the 25 or closer to the 36? So 29 is 4 away from 25, but it's 7 away from 36. So I would say square root 29 should be a little bit closer to the square root 25. So I'm going to say it's closer to the 5 than it is to the 6. Now, this is going to help us estimate the number. So I need a number that's bigger than 5, but smaller than 6. So I'm going to estimate it to be, approximately 5.4. 4. Now, not every one of you is going to get the same answer. Some people might say, oh, I think it's going to be approximately 5.3. Some of you might say, I think it's going to be approximately 5.5. That's okay, because the point of this exercise is just to get an estimate, okay? So if I was wanting to estimate square root 50, I would look at my list of perfect squares, and I want a perfect square that's a little bit smaller than 50. Look at the list and see if you can find one. All right, hopefully you said that was square root 49. It's a little bit smaller than 50. So the next consecutive perfect square after 49 is 64. So there's our two perfect squares. The square root of 49 is 7. The square root of 64 is 8. So I know if I wanted to estimate the square root of 50, it would have to be a number that's between 7 and 8. Now, which one is it closer to? Is square root 50 closer to square root 49? Or is it closer to 64? Well, hopefully you said square root 49, because it's only one away. In fact, it's very close. So I'm going to try to get it really close there, and I'm going to plot that on the number line. So square root of 50 is closer to the 7. So we're going to approximate that. Since it's only 1 unit away from square root 49, I'm going to say it's very close to 7. So maybe something like 7.1. All right, that's my estimate for square root 50. All right, problem C. I want you to pause the video and try this problem on your own. All right, welcome back. Let's see how you did. So if I'm estimating the value of square root 120, I want to pick a perfect square that's smaller, a little bit smaller than 120. So hopefully you said square root of 100. And then the next perfect square after that is 121. The square root of 100 is 10. The square root of 121 is 11. So I know the value of square root 120 has to be a number between 10 and 11. But I also want you to notice that square root of 120, that is very close to square root 121. So it's going to be closer to the 11. So if I was going to estimate it, I want a number that's between 10 and 11, but it's closer to the 11. So I'm going to say, approximately 10.9 or so. Maybe you put 10.8. That's fine. Okay. All right, example 5. Create and label a point on the number line below to represent an estimate of the following irrational square roots, and then give a decimal approximation for each. So before I plot these irrational square roots, I've got a number line here, and what I want to do is put my perfect squares on the number line. So I know the square root of 9 is 3, the square root of 16 is 4, the square root of 25 is 5, the square root of 36 is 6, square root 49 is 7, square root 64 is 8, square root 81 is 9, square root of 100 is 10, and the square root of 121 is 11. Now, knowing these perfect squares is going to help me figure out where to place each irrational square root. So, for example, the square root of 15, that is very close to 16. So I want to put it like right here, and I'm going to label that with point A. So point A is a number between 3 and 4, but it's closer to 4. So maybe something like 3.9. Again, this is just an estimate. All right. Square root of 108. That's bigger than square root 100, but smaller than square root 129. So I'm thinking might be somewhere like right here. I'll put a B. So square root of 108 is got to be bigger than 10, but smaller than 11, and it's closer to the 10. So I don't know, maybe 10.2, something like that. All right, square root 32. Square root 32 is bigger than square root 25, but smaller than square root 36, and it's going to be closer to the 6. So this would be point C. So my estimate for square root 32 is a number between 5 and 6, but closer to 6. So maybe 5.7, 5.8, somewhere around there. Okay. All right. Pause the video and try problem D on your own. All right, welcome back. Square root 54 is between square root 49 and square root 54, but it's a little closer to the 7. So I'm going to put it right there, and I'm going to label this point D. So I don't know, approximately 7.4, 7.5, somewhere around there. All right. All right, example 6 is an example of how this concept might be tested on a standardized test. And I want to show you how tricky they made it. So point M is shown on the number line. Which value is best represented by point M? So when I looked at point M, the first thing I wanted to note is how is the number line scaled? Well, it goes 6, then a blank tick mark, 7. So I know this is 6.5 and this is 7.5. So I know M is just a little bit smaller than 7.5. So I'm going to say M is approximately 7.4. Now, look at answer A. Many students were tricked into choosing answer A on this particular standardized test question. But A doesn't say 7.4, it says square root 7.4. So I'm going to grab a calculator and I'm going to put in square root 7.4. 7.4 is equivalent to approximately 2.7. So there's no way that could be the answer. All right, let's go to answer choice B. Square root 65.2. Approximately 8.1, so that's too big. All right, let's look at answer C. Square root 55.3. Oh, approximately 7.4. So that's the answer we're wanting. But again, I hope you can see why many students were thrown off guard by answer A. Maybe they were working the test problem too quickly. They didn't really think it through. And that concludes today's lesson, Estimating Irrational Square Roots.